there, science fans! Today we're diving into the world of magnetism, the EM spectrum, and waves. Because who doesn't love a good wave? Hi, Grandma.
Did you know that without electromagnetic waves, you'd actually have to talk to people face to face? Scary, right?
Magnetism works in many different ways that you might not even know. For example, the Earth itself behaves like a giant magnet. Its magnetic field protects us from the solar wind by deflecting charged particles from the sun. Oh, we're doing that?
Oh wait, we're now going to create an example of magnetism through an experiment. Okay, let me clap. 1, 2, 3, 4.
Okay, so in this section of the video, Mia is demonstrating how these magnets are working, but you are seeing the magnets work, but you're not really like knowing what's going on. So there's a lot of different things that are happening that you don't really see, such as the dipoles. These are objects or molecules that have two opposite charges or magnetic poles, but are separated by a distance. So a good example of this would be the magnet that she's showing right here. Another thing you're not really seeing is the magnetic field around the magnet. It's the invisible force or electric current or changing electric field that exerts a magnetic force. So that's what's basically making the magnet magnet. There's also many other materials that we see but we don't think are magnetic, but actually are. They just aren't magnetic at the moment. Materials are called paramagnets. They are weakly attracted to the magnetic field due to the unpaired electrons in the material, but when they are paired, it's when they're paired in magnetic domains, if that makes sense. Basically, it's the region within the material where the magnetic moments of the atoms are aligned in the same direction. So you can see that in this video right here is a amazing example of exactly what I'm talking about. The magnetic field lines are also considered when looking at magnets. They are visual representations of the directions and strength of which the magnet field is flowing through. There's also the magnetic flux, which refers to the total amount of the magnet field passing through the surface, how strong the magnet is.
Right here, we got the EM spectrum. We begin with the radio waves, and then as they fade out, it turns into microwaves. The microwaves start off weak and then begin to get stronger. Right here, this section is the only part that are visible to our human eyes. And then this part, they are used in medical fields.
Hey, so now for the boring part. So this is our formula triangle for velocity. So frequency is measured in hertz, velocity is measured in meters per second, and wavelength is measured in meters. How it works is these two down here multiply and these divide. So if you were looking for velocity, you would do frequency times wavelength. If you were looking for frequency, you would do velocity divided by wavelength, and so on. And then our wave speed is always going to be wavelength divided by time. Per second.
Hertz.
Yes, go.
If a wave has a velocity of 6 meters per second and a frequency of 3 hertz, what is the wavelength? So for this problem, they already give us our velocity and our hertz frequency. And so we're looking for wavelength. So as you can see here, we're gonna have to put 6, our velocity, over 3. And that will equal to our wavelength, which is 6 divided by 3 is 2. And so that would make our wavelength to 2. Yes.